Okay, now we can pass the next discussion, which will be led by Dr. Garcia Nocetti. He studied mechanical engineering and electronic engineering at the UNAM. He has a master's in sciences and a PhD in computer system engineering at the University of Wales in 1988 and in 1991 as well. He did a postdoc at the same institution and at Sheffield University between 1991 and 1992. He is a researcher at the UNAM. He is a member of the Institute for the Study of Applied Mathematics of the UNAM, where he's been head of computer and automatization systems from 94 to 2000 and as director of the Institute up to 2012. He has been the head of engineering at the UNAM. He has been visiting researcher at the program for the duct or pipeline developing system of the and in Mexico, and also now works at Infotech. It's worth mentioning that the arrival of Dr. Fabian Garcia Nocetti for this institution has been very timely. It has come as a great time because the momentum of this topic and this seminar. Well, Dr. Fabian Garcia Nocetti has taken this under his wing. I think this is worth thanking him for and recognizing. Without further ado, thank you. And also I'd like to thank the authorities for their kind invitation and the organizers, Infotech and INEGI. We also have very close friends there. We've had them for many years, and in this sense, it's of course very important to discuss this issue, particularly because, and well, for me in particular, it's very nice to rethink computing. We started many years ago, as Elio mentioned, working on parallel architectures when they were still not designed in silicon. They were emulators of parallel architecture with programming languages which many of you may remember, such as OGAM, ADA, etc., in which the idea of programming processors in parallel was done not in a very friendly way. You had to deal with a great amount of concepts, a great amount of instructions to do communications between processes, something which is done quite transparently now. It's worth mentioning this, notwithstanding, because there's been a huge evolution in this sense, and this leads us to the use and appropriation of technologies to solve strategic issues pertaining to big data. Let's discuss high-performance computing because it's very closely related to big data. Okay, in this sense, we will discuss high-performance computing. Okay, this will lead us to analytics and also software for big data, and a case study which has been managed or presented as a test of a concept, and then also the development of an application for the case of petroleum engineering. And then we'll have our conclusions. High performance computer is the use of parallel processing to execute applied no advanced applications in an efficient, trustworthy, and swift manner. But how can we ensure that we are segmenting a problem as a series of parallel processes? How do we know? How can we assign these activities to the architecture of the corresponding hardware, and how can we ensure that we are truly going to work in the implementation, and what's the minimum number of processors that we're going to require to truly conduct this activity? The term is applied for their flops, and it's also used as a synonym of supercomputers. Sometimes this is not the case. Sometimes some supercomputers use more than one petaflop. Who are the users of high-performance computing? Well, researchers, engineers, academics, and well, of course, the military. They use high-performance computing. The more demand and speed of the processor, the more interest for agencies, companies, processing transactions through data warehouses. This is it's a very sensitive topic. So we have a large collection of high performance computing for modeling prototypes, weather, etc. This is very important because modeling prototypes, working with physical prototypes is expensive and time consuming. The use of high performance computing through modeling simulations allows us at some point to create adequate models that are similar to the original one, and through manufacturing processes it helps reduce the cycle of process of these applications. And from lobby data, which is a issue that brings us here today, the benefits in innovation. Well, just to mention a few. If we use of the time adjustment for a laboratory, that can take us 9 months to a year. However, with technology of this nature, it can take less than a week. In the case of a component, well, it costs $50,000 on average, but in a lab, with techniques of this nature where it can be done for less than $3,000 through large-scale modeling and other technologies which accelerate the process. But we consider that this improves the engineering of different business applications, such through data mining, logistics, etc. And then another important consideration is the high performance economy. The total value of the world market in 2010, it was 26 billion pesos, and the next year it's going to be 30 billion. Models through computers, okay, yes, the cloud and such, and resources in the cloud are more and more accessible, meaning consumers consider this a commodity. It's important to mention some obstacles which are associated to this, and therefore also the issue of big data. First of all, there is a problem with data scientists. It's important First of all, we need specific training for them. Currently, they are forming these specialists in strategic issues, but through specialized training, postgraduate studies, etc. But there is a demand, there's a large demand for information scientists. Also, we have codes and technicians who work on this. There's a lag in the creation of new codes, and there's a gap between faster programmers and other systems. Companies see these technologies more as a cost and an investment, and especially because of the difficulty of measuring the return on investment of something of this nature. What is big data? Well, these topics have been defined this morning. So it's something important in this sense. It's important to mention that big data is associated to the data that goes beyond the size of the tools. And this is perhaps what makes a difference between handling problems in the real life in a conventional fashion through a certain type of high performance computing with conventional techniques, and doing so in a different way. So how is this originated? Through an explosion in the diversity of data and speed and data generated in real time as a result of these technologies. And well, what's it good for? Well, it allows us to generate knowledge. So we have different types of data. We've seen during the morning session the different type of data associated to this platforms. This implies that we are living in a time of data abundance, and it has reached all sectors of the economy. Data are a way to learn about the human nature, and creation of value through effectiveness, competitiveness, etc. is also immediate. In 2010, it was then estimated that this industry had a value of more than 100 million, growing, 100 billion, and it's growing at 10% yearly. So that's why there's a growth in the importance in every sector of the economy. Big data for the creation of value, segmentation of the market, and innovations, new models, etc. Something that's fundamental that we must consider is that, and this is also a problem, are aspects related to transparency and efficiency. So Dr. Vincer had mentioned this before, and this is where we have an area of opportunity, and there's a long way to go, especially when we refer to open data. The issue of analytics of large data refers to the methodologies to transform these large amounts of data into useful data, into data that can provide us information, and in this sense, with analytical purposes, to create decisions on the basis of these. The term analytics or computer analytics, it originates in biology, in intensive biology, in genetic engineering particularly, and then into algorithms to detect patterns, tendencies, correlations, and various space-time horizons based on conventional techniques, which has been present in this sense. So this has been associated to visualization techniques, which complement these capabilities. So this presents a series of problems, but one of the most important ones is the availability of data, because we have asymmetry. Governments create open data, governments open this, but just slow by little, and the information of data is so closed. Different capabilities for this, and this is part of the problems that are generated. Privacy and limits of data clusters. A good amount of the new sources of data reflect perceptions, intentions, and desires. So we must ponder on this. Something that's also important is what we call not confusing, and sometimes there are patterns where we don't have massive amounts of data. Up to what point can we truly identify useful information and are we not becoming confused with patterns that don't exist? What happens when traditional analytical techniques, there's a point when data mining doesn't provide the solutions we expect, and how do they face the challenge of the large risks? So in this sense, we've generated, of course, and here is where the importance of data science it comes into consideration, of treating information from a statistical viewpoint. Science is based on an algorithm applied to the big data problem, but it implies finding a correlation, applying algorithms, providing greater visibility levels that transform. I had contact with an organization and the possibility of analyzing capacities, and this of course is fundamental and something which is necessary from different organizations to incorporate the sense of data in the organization. Every time, the fact that we have specialized staff in data analysis, such as a scientist with scientific basis associated to this, becomes fundamental, and from this, this is why it's important to generate human resources in the area.
Because then data scientists become a fundamental piece, precisely as an interface between the particular issue and the way in which it is solved. Thereafter, it has been necessary to create tools, to develop tools, and software development oriented to distributed computing. And one of the first options, there have been options that have emerged before others to solve the issues we have briefly presented in this regard, and that are associated to big data and the development of data science. It offers the capacity of local processing that enables to escalate from local servers to thousands of machines, allows distributed processing of large data sets, as it has already been said during the previous presentations. But the two concepts which is supported are the map-reduce technique as well as the distributed file system. These are two fundamental components that help us to efficiently address problems that, due to their nature, cannot be addressed efficiently with conventional techniques. The main features of MapReduced are precisely the issue of distribution and automatic parallelization. Formerly, this was done heuristically. After that, Other parallelization and distribution techniques were developed for processes, for processors, in a somewhat more efficient manner, with a very direct influence of the systems programmer in order to perform charge balancing tasks, process distribution in different processors, and so on. This reduces the complexity of this sort of technologies. And another fundamental aspect is the tolerance to failure and redundancy that allows the system, which is very complex in nature, to continue to work even during failure, which takes place at different stages of the process. Transparency and scalability, well, these are aspects that are also facilitated by these technologies. And data localization, well, the algorithm is displaced to the data and not the other way around, and that is one of the main differences compared to conventional techniques. Also, monitoring techniques are available, which are essential precisely to assess performance aspects for this type of systems. Summarizing the big data stages and the solutions with Hadoop and other alternative tools are precisely to first discover where the big data is. We need to define what is the data that interests us, find the sources, if this is historical sources or social media, among others, record the data in the system and determine how this will be processed. That would be the first stage. The second would be to extract and clean large data volumes, and it is precisely about extracting the data from the source, profile and clean the data as well as make them suitable for the needs and apply quality standards for them. Another important stage is structuring and analysis of big data, giving the treated data a logical structure to store them at the chosen repository and find the available data to find correlations. Also data modeling, which specifically the application of algorithms to the data in order to apply statistical processes and to solve the petitions or requests launched through data modeling based on data mining techniques. And then finally, there's interpretation of big data, interpret different solutions and contribute with a final result. This, of course, with visualization techniques that enable us to make the results visible and to make the decisions accordingly. This is one of the aspects that are needed in order to implement or start working with this sort of platform specifically. And just to finish, a case study, what was first used as a concept test to experiment with different types of tools, but specifically, given its degree of complexity, from the standpoint of the large amount of data that this issue has, is, for example, the study of seismic data to detect fractured deposits using seismic information for that purpose. And the particular topic was the use of self-organized data, neural networks, and organized maps, as I said, to carry out this project. This project was developed at IIMAS, the Research Institute for Applied Mathematics and Systems. Dr. Benitez Perez is the current director of this institute, and we're collaborating with them, of course, on the side of high-performance computing. Basically, this is a graphic analysis methodology for seismic information based on the issue of self-organized maps and neural networks. The idea is to aid petroleum engineers or specialists to recognize areas in which oil might be present, areas that are, of course, constituted based on the information and seismic profiles that are obtained as input information. In this regard, the methodology is begins with a seismic cube, and it includes at least one of the oil wells and what is called a geological horizon, and that is a surface made of rock that have similar or almost the same features and that were accumulating by layers with time. And we could think about a seismic profile in that regard, a geological horizon as a surface that has similar characteristics. In this regard, this seismic record produces a wave that is created by an explosion. It gets in contact with the medium, and there are receivers that would then record the seismic trace. A large number of this seismic information collection produce what we know as a seismic gather. And what we have here is a seismic cube produced by a set of these measurements in association with the profile, with the petro profile. And the information that is produced by this technique is enormous, especially for the case we're discussing. We're considering a database of around 100 gigabytes, but seismic cubes are actually one or two orders of magnitude bigger than this. But that is information available, seismic profiles, and with that, the idea is, if we know that on a geological horizon there is a deposit, we want to know how the neighboring area to that well behaves, what are the features of the soil around it, so that we can infer that in the vicinity or within that same profile or horizon is where we could probably find other types of wells with the same features. And well, that is the issue. In this case, we have the necessary information for all the gathers that are the actually processed information. The Fourier's transform is used for this purpose, and in this case, self-organized maps are a type of neural network that is trained using unsupervised learning, and that can be done offline. Actually, all the conditions exist to do this offline, so that when a neural network is already trained, then time will not be lost on that. Also, this also produced a discrete low dimension representation of what this is. These maps are different to other neural networks in the sense that they use a vicinity function in order to know precisely if in the vicinity the topologic features are similar. And that is useful for us to know what we're talking about and to know the horizons we're working on, which might have the same features. This is a representation of a cluster of 32, drawn on a cluster of 32 nodes, several nuclei per node. Each one of them has a terabyte and RAM and 32 terabytes of hard drive. the seismic cube or the sub cubes are distributed on the corresponding nodes, and in that manner we obtain the profile and the horizons that have similar colors are those that show similar features. Here you probably appreciate these three black lines. These three black lines are precisely where productive wells are located, associated to this field. And right here we can see a representation of that seismic cube with the three corresponding wells. The issue here is that different classes are assigned to different horizons, to different depths. Here we see this in red. There are again three lines that represent wells, and at certain depths, as we can see here, some are precisely class 8. And there the wells precisely touch that red mass, and that is representing is that precisely there is where we find the deposit that is currently being exploited, and in the red areas it is possible that there are corresponding deposits, similar deposits. Therefore, it is very likely that we might find them there, and it is a very direct way to perform a good analysis and be able to determine when the necessary preparations or where the necessary preparations are needed to make sure that an oil well or actually an oil deposit might be found. This is research in progress. We already have preliminary results in this regard. It is, what we're actually doing is a geometric analysis, not a physical or causal analysis. And these tools, this methodology is being tested against other methodologies that had already been tested. However, we have had good results with this. There is a new development that is currently being evaluated in PEMIX, and this is just a sample of a very particular case study showing how these high-performance big data analysis components, as well as visualization components, enable us to solve a practical problem that is also an issue of strategy. And that is all. Thank you. Thank you very much, Dr. Fabian. As you remarked at the end, this work you were showing us about the production of oil wells that combines data mining techniques, information visualization, and grouping of information is precisely an example of the power that analytical tools might have when the equipment and human capital is available, as well as the knowledge of how to use these elements. This morning, superhuman capabilities of high-performance computing were being discussed, and well, also the capacities of artificial intelligence were being discussed, because these provide us with an important use potential to solve real-life problems, as Dr. Incera also showed us.